we get going. Some of you have turned in proposals already. Thank you very much. It's awesome. I've responded, I think, to all the ones that have been turned in. Maybe I missed one, or I'll take a look. But they're due at the end of the week, end of the day on Friday. It's not a huge lift here, I don't think. It's just pick something to do, describe it, and then I will approve it. And the way that you know it's approved is that, I'll write a note to you in Canvas, but you also get a point, 1 point. So it's an extra credit point since the assignment's out of 0. So you're welcome. Yeah.
I didn't get the point.
Yeah, I haven't looked at yours yet. I don't think. Is it turned in? Is it turned in? For your proposal? Yeah. When did you turn it in? That's wrong. Any questions about, I don't know, anything else so far? Homeworks? We got a new homework up. I put the due date on that, already anticipating the ask as the Monday after the Thanksgiving break. So it's not the Friday of that week, but the Monday after, okay? So good luck on that. There's an R&N activity homework, and there's a GAN homework as well. And that we haven't done GANs yet. That's what we'll be doing in the next couple of lectures. That'll come up here. All right. Well, I guess we'll get started then. All right. So we're gonna start doing what I'm calling generative convolutional neural networks. So we've just looked at these recurrent neural networks and transformers, and many of them are generative in the sense that you can use them to generate text, right? So like, all the RNNs are this way, in the way that you typically train these, like the kind of tasks you typically train them on, right? Like you give them like some input, and then they produce the next token in the sequence. And the transformers, the decoders of the transformers do the same thing. They learn to do this in this autoregressive way. So those are generative models. They're generative for text or any kind of sequential data that you're training on. We're gonna like do the same kind, or have the same kind of concept, but now do it for convolutional neural networks. So they'll be generating things like images. And so we're going to talk a little bit today about like what does it mean, this like generative idea? How does that fit into like the machine learning framework? And then we're just going to go through examples of ways of generating images. We'll go through like the most basic example today, and then we'll start building up and doing things like variational autoencoders, variational autoencoders, GANs, adversarial autoencoders, and then we'll finish up with some things that are not generative but kind of have a similar flavor. These like self-supervised contrastive models that are really popular right now. So that's where we're going for the next couple of weeks. As always, just stop me and ask questions as you got them. Okay, so really up to this point, everything we've done is pretty much, supervised. Supervised in the sense that our data comes in these kinds of pairs where we have like X here. I have this pair XY where you have like X, which is your actual like data, and then Y, which is some label or something about the data that. And usually, what you're trying to do is you're trying to learn that relationship. You're trying to learn the map from some function that maps you from this data to that label. And this is what supervised learning is. And pretty much everything that we've done so far looks like this. Obviously, like classification, the like object detection, and the segmentation, the captioning, all these things are these examples of learning maps from X to Y. When it came to the transformers and the way the transformers were trained, also like for the RNN where we were doing like seek to seek, right? We have the X and Y here were like the input, phrase from the language, and the Y would be like this target phrase in the other language. But these, like the transformers, like we were talking about how we train, like the BERT, like a BERT model or something like that, is something that is a little bit different from supervised. And we're going to kind of go through and talk a little bit about how that's different in these next couple of slides. But so far, really, what we've done is this: supervised. You got this pair. Your whole goal is to learn this map from X to Y, and like in a real way, you can think of like a lot of what we're doing in like deep learning as like using neural networks as like a general family of functions, like representation of a general family of functions, and you're trying to find the best function within that family of functions for doing this task, mapping you from X to Y. So it's like a function approximation in some sense, is like what we've been doing. Right? So all these examples that we've worked with. Okay, so there is another kind of learning called unsupervised learning. And in unsupervised learning, you're learning to do a kind of task, but the task is not to learn this map from X to Y, because you no longer have a Y here. There's no label. You just have the data X. So what are the goals or tasks in that kind of setting? Well, they're usually, what you're trying to do is take that whole distribution of data represented by your data set and learn something about the underlying kind of structure of that data. So maybe this is something like images, and what you want to be able to learn is like some like lower dimensional list of factors that represent what's in that image, and that you could say use to like actually generate the image itself. Something that like represents like fundamentally what's in that image. And examples of what we would be doing with unsupervised learning would be like clustering, like what learn some underlying structure of the data, use that underlying structure to like cluster and see like what things are similar to each other. If you've done some machine learning classes, otherwise you almost certainly ran into something like called K-means clustering. We've done it in our class. Actually, we did the K nearest neighbor models. There's the idea here again is to say like, is there a way of without any sort of supervision, learning something about how our data is structured? This sort of Mickey Mouse data set here, you might be able to learn that there's kind of 3 different, globs or clusters of things there. Another form of like unsupervised learning is this notion of dimensionality reduction. So you probably, again, if you've really done any kind of a numerical analysis, but also maybe done another machine learning course, you might have seen principal component analysis, which is a method of doing dimensionality reduction. How do you what does that mean? Well, for PCA, it's there's a way of picking out in your data like subspaces in your data space that like encode the most variability in your data. And then the next, so that corresponds to one principal component. Then in the orthogonal complement of that, to that principal component, there's maybe the next component explaining the most variability in an orthogonal direction and so forth. But in general, you can, there's this idea that, and the way you do dimension reduction in PCA is that you kind of figure out all these principal components. It's basically a change basis for your underlying vector space, but then you just keep around the principal components that like encode the most variation, and so you're going to lose some variation in your data, but not a whole bunch. If you drop off like those that just only explain maybe 10% or less of your data. In general, though, like what this means is that there's like an underlying structure to your data that is lower dimensional than the data is presented to you. Things like like images are really high dimensional, right? So like 224 times 224 times 3, like that's a really high dimensional space. But it might be that you can kind of describe what's in those images in a much lower like dimensional vector. And so, like in general, in unsupervised learning, you're kind of wanting to maybe learn something like that. Like, can you tell what is the lowest dimensional, good faithful representation of your data? We're going to spend a lot of time in the next couple of lectures talking about things like autoencoders, which is like the nonlinear kind of PCA, where you're compressing your high dimensional data down into low dimensional data, and then trying to use that low dimensional representation of your data to like reconstruct the original data. And the better you can reconstruct that, like the more faithfully you're representing the original data in those low dimensional features. And we're going to go through the mechanics of that. A lot of times, what we're doing when we're doing unsupervised learning is that we think about our data as like a distribution of in some high dimensional space or whatever, some ambient space. It's a kind of distribution, and it has for certain configurations in your space. So like for certain configurations of the pixels in like pixel space, those correspond to like natural images that you would expect to see in the real world. And you can think of that as like your distribution being very peaked around that configuration of pixels. But as you move away from that configuration, it might be that like it starts to look less and less like a natural image until they change enough where it now looks like another kind of natural image. And so in this kind of high dimensional space, you might have a distribution describing what it means for a configuration of pixels to be in your data set, and you're trying to learn that distribution in this like this sort of non-intuitive high dimensional space. And so that so that you can do things like sample from this distribution, sample examples from a probability or from your distribution over this, like for example pixel space. So you're sampling images that might not have been in your training set, but for some reason what you've learned says that like this is something like that should be in there. And so maybe it looks like a natural scene. We'll be learning methods for doing that, like generative adversarial networks. Right, so side by side, supervised and unsupervised. Approaches like BERT, where we take data, so like in like those language examples, we take these phrases and then we kind of like mess with them. We kind of distort them, right, by masking some of the tokens or like just like randomly replacing other ones, and then trying to predict the original phrase from that corrupted phrase is a kind of unsupervised approach as well. Mainly because you've only used the data X to like train itself. However, if you think about it, it's like there's still a supervised signal there. Like you're supervising the training of that network with the data. So it's like a supervised problem where the labels are the data itself. But we think of that as like unsupervised, or a phrase that's become more popular in the last couple of years, self-supervised. So now there used to be like there was supervised, there was unsupervised. There's like reinforcement learning, which is something different that we'll talk about in a couple of weeks. And that we thought of those as like the major areas of machine learning, but now self-supervised kind of sits in there as like somewhere between supervised and unsupervised. And of course there are iterations on these things like semi-supervised, which is also between supervised and unsupervised, where some of your data has labels and some of your data doesn't. So anyways, there's a lot of kind of terms that have related ideas, but in general, we think of something like the BERT approach as being unsupervised, or what's more popular to say nowadays, like self-supervised. What's great about unsupervised learning over supervised? Well, you would typically think of this as like, these are like the canonical problems that we usually think of when we think of machine learning. But there's a problem here, right? You need labels. Supervised learning needs labels. And even though we talked about a lot of amazing data sets that are like publicly available that have lots of labels, those were actually quite expensive to create, right? I mean, in some sense, you had to have a whole company created that, like, you know, provides like a photo upload service that, without your knowing it, you know, got you to sign an agreement that said that they could use your photo for whatever, including training machine learning models. And then somebody had to go in and like hand label those things. You know, the hundreds of thousands, millions of images. That's, you know, some wealthy company was able to like do that kind of thing. But in general, you're going to find that you're not going to be able to do that kind of thing without a whole lot of resources. So maybe one day you'll have a fantastic company that can pay to have all their data labeled. But in general, this is an expensive thing to do. And so there's a real hope that we can do the kinds of things that we do in supervised learning in an unsupervised way. Like we can like learn, like for instance, in like the class, like think about ImageNet. We want to be able to use just the data itself, not its labels, but and learn an underlying structure of that data, such that we actually can use like that underlying structure to do this task, this classification task, in a really like, you know, excellent, maybe even state-of-the-art way in terms of like, you know, like accuracy or, you know, top one error rate or something like that, right? Like this is the kind of hope that we have for unsupervised learning, mainly because it would allow us to skip this step of having to create the labels. But you can imagine, like in general, this is difficult, right? Because unsupervised is exactly what it sounds like. There's, you know, it doesn't quite know what kind of structure it should learn to do these tasks. Whereas when you have these labels, it allows it to pick up just the parts of the data that's needed to do, you know, to predict this label. So you know, if you follow like any of the big like machine learning research groups, you'll know that like Facebook is really into unsupervised learning, actually really self-supervised learning right now. We're like, you know, Jan LeCun leads that whole research organization there at Facebook, and they really spend a lot of time trying to figure out, you know, how can we do the things that we've been doing in supervised learning in an unsupervised or a self-supervised way. And actually, in a couple of lectures when we get to self-supervised learning, you'll see some of the approaches that they've put forward and others that actually have quite good results on some of the data sets that we're now familiar with. And you know, like this, just one more call out here from this slide. If you in general can do unsupervised learning well, then you are probably learning, you know, some really good underlying structure of like how, you know, I'll say the world, or just like how the universe, describe how your data set is put together. And that should be useful not only for like a particular, you know, classification task, but all other tasks that you'd be interested, you know, in working on in that universe. And so it's far more general in that sense. Okay, questions so far? Makes sense if you've done like a machine learning course or spend some time just in machine learning on your own, you'll have probably seen these two concepts and know something about it. Okay. So now I want to talk a little bit about generative models. So generative models sort of sit in this camp of unsupervised learning. And the idea here is that we want to, in general, what we want to do is we want to be able to either learn a model that is the distribution of our data. So again, you know, one way to think about your data sets is that they are samples from some probability distribution over like a larger like space of things. So like again, like for images, this is like somewhat straightforward to think about. You could think of like all your images are of a certain size, right? Maybe it's standard 22 or 224 by 224 by 3. And each of those, you know, so you can, and it's 8 bits, so you have 256 different values that can be taken on in this like tensor of size 224 by 224 by 3. So like any kind of random, any kind of random sampling from like that distribution or just from that uniform distribution there is like an arrangement of pixels. But not all of them are arrangement of pixels of like what's in the ImageNet, right? So so sampling uniformly just is like everything's a member of this set. But what you want to think about in terms of like what represents a data distribution is that distribution becomes peaked around the configuration of pixels that represent the images in our data set. These are actually CFAR images, but whatever, like the CFAR, the ImageNet, whatever that data set is, you want to think of this as like your data distribution is peaked around the arrangements of pixels that correspond to samples from your data set. And what that means is the peaking means that you're more likely to sample from that, right? Like there's a lot of probability assigned to a certain arrangement of pixels, and no probability assigned to other arrangements of pixels, and that's like a data distribution. That's that's a way of thinking about how a data set can be thought of as like samples from a probability distribution. Now, we might be interested in learning to sample from that. Not sample just like the sample we have from our training data, but to sample generally from whatever the true underlying distribution is of our data. So what we want to be able to do is learn a model, either explicitly, where like this thing can generate, images, for instance, or we have another kind of procedure where we learn something that just generates samples from it. So it could either represent the probability distribution explicitly for any arrangement of pixels, for instance, or there could be, it would just give us samples from that distribution. So if we are learning a model that allows us to sample from the data distribution, then we're doing something that we call generative modeling. We're learning a generative model.
Is it similar to knowledge distillation that we do learning distribution?
So say it one more time.
Is it similar to knowledge distillation that we do learning distribution?
I'm not sure what you mean by knowledge distillation here. Okay. If you want to ask me about it like after, that's fine. I'm not totally sure. Okay, so like this is starting to feel like really different now. Like so we talked about unsupervised learning that we haven't really done, except for I mentioned like BERT and these language models being like that was like unsupervised learning. Now what we're talking about is a different kind of approach here, where instead of learning like these supervised maps from data to labels, we're talking about like learning the underlying structure of our data and being able to generate samples from that underlying structure. So this is what we call generative modeling. And yeah, sorry, should put this up already. These are the two different flavors I was just talking about. You can actually learn to model the probability distribution explicitly, so it's going to give you like a probability for each configuration of pixels, for instance, or implicitly, so you can just you're just sampling. Like it'll give you a configuration of pixels that should be from this model or from this data distribution. And we saw these with language, with text. That like GPT, everything in the GPT family. You give it some initial seed sequence of tokens, and it starts generating more and more and more. And as you move up through the numbers in the GPT family, like it's getting better and better at doing that. I showed you examples, and you're probably aware of these already just from your own reading and things like that. I showed examples at the beginning of the semester, I should say, of like amazing ability to like generate, for instance, like faces. So these are arrangements of pixels that look like faces, and remember we looked at like celebrity faces. I made this joke about me being whether or not I was in that distribution or not, but at the very beginning. But in general, like what these models are doing is they're like learning to generate, say, the arrangements of pixels that look like faces that are like from that distribution of celebrity faces. And there's a whole bunch of like other kind of famous examples of this. This is the LSUN data set, which is literally like interiors of of homes, bedrooms and things like that. There's like lots of generative models in computer vision right now. People can generate artwork, they can fill in all kinds of, like, they can colorize, black and white images, they can like fix, parts of an image that might have been ruined, like an existing photograph that has been ruined, things like that. These are all done with generative models of some kind or another. And here's kind of a taxonomy of generative models. I already talked about the explicit and implicit density. So explicit meaning you're actually learning the probability distribution, like how to assign probabilities to configurations of things, and implicit being the sampling from the underlying distribution. And over the next little bit, we're going to really focus on three kinds of models. So we're going to talk today about these pixel CNNs. We will talk then about variational autoencoders, and we'll talk about GANs, these generative adversarial networks. You've likely heard of at least GANs, maybe variational autoencoders. Probably not pixel CNN because it's kind of silly, but it exists nonetheless. But there are other kinds of models like within these families of things, and we're showing some of the other ones here. Maybe not heard of, maybe have, maybe haven't. Somebody was asking the other day about belief networks, and things in this family here are belief nets, but they're fully visible, meaning that there are no like latent variables. So this is like the easy situation to be in when there are latent variables. Just for like the people that we had the conversation with, that's what requires the like other kinds of algorithms that aren't these feed-forward networks. Okay, so this is where we're going. We're going to talk about generatives, convolutional networks, how to generate images in particular, and we're going to be focusing on these kinds of models. Questions? No? Okay. All right. So, the first thing, so we're going to talk about these things called pixel RNNs, pixel CNNs, and the way we're going to think about these. So these are within that family of explicit density models. So we're actually going to be learning a probability distribution over whatever the data ends up being. In this case, it'll be like in the CNN case, it'll be arrangements of pixels. But the idea is the following: is that the way that we're going to learn to do this is we're going to take here's like the thing that we want to model. We want to be able to assign a probability or a likelihood of a particular image being part of our data set. So think of this as being like the full arrangement of pixels. However many pixels there are, 1 through that number of pixels. And the way that we're going to do this is we are going to do this in like this autoregressive way, which is we're going to use rules from probability, this sort of chain rule of probability, to turn this like single distribution into a product of many conditional distributions, where the conditional part is we're going to learn a whole bunch of these distributions that predict like the next pixel value from all the pixel values that we've seen before. Now this is kind of weird, right? Because there's not really like a good ordering to pixels, right? I mean, this is like the whole reason why we weren't doing RNNs and transforms and things like that on images, because there's not a sequential nature to them. Nevertheless, we're going to like force a sequential a sequence, like an ordering to the pixels, and we're going to learn to do this thing nonetheless, right? So this is usually going to look like the raster scan kind of ordering, right? We're just going to like start with the pixels from at the top of the image, go from left to right, and go to the next row, left to right, the next row, left to right, and so forth. Obviously, you could like do this in any order if you wish. Maybe there'd be some advantage to changing that from there, but in general, this is something you could do, and it allows us to get at. This gives us a way to actually learn a model like this from our data, because we can't usually go straight to something like this, at least not with the kinds of models that we're talking about here. Yeah.
What is the first one in the product?
Oh, yeah, like what's the first pixel?
Yeah.
Yeah, so that's like a, you know, that's you can think of it as a kind of like prior on like what you expect, you know, pixel values to be, like in particular like that pixel value, like in the top left corner. You know, in general it could just be like a prior for any pixel in the image, but the top left corner might be different, you know. But yeah, it's a kind of prior. So it's something that you can like look at over all your data and compute, right? And just say like, in general, you know, with probability, you know, this we expect the pixel to have this RGB value, you know, and then you have that kind of empirically assigned across, you know, all the possible RGB values. Yeah, good question. You can also, just like you can do in a lot of different settings like this, is that you can make some kind of assumption. You can make like a maximum entropy assumption, like this is like a uniform distribution over all of your pixel values, and then as you run the learning algorithm, like that'll be adjusted. So, you know, why would we even do something like this? Well, it's a good question. It's a fair question, but it at least gives us some way of thinking about how to explicitly model the distribution here. In fact, this was really like the only way to do this until you know, a couple other techniques came along, again within like the last decade. For images.
Sorry, what is N?
Yeah, that would just be like the total number of pixels in the image.
Okay.
So like, you know, we're picking some ordering. Again, just think of like a typical raster scan ordering, and just going, you know, 1 through N. Yeah. Good questions. Thanks. Any other questions? Yeah.
Yeah. So we just predict the 3 channel values and we try to combine them. So it is kind of like 3 times.
Yeah. That's right. So this would be like an RGB triple here, like, you know. A triplet of integers between 0 and 255. Yeah. But of course, that could change if your images are like have a higher bit rate, or you have more channels because you're not doing natural scenes. You're doing maybe like something coming off a microscope that had multiple, you know, more channels, like hyperspectral channels. I don't know, whatever. In general, you know, this is a general setup for you could adapt this to many like pixel setups. Yeah, so how are we going to do this? Well, you know, each one of these things is going to be a complicated function of like what happened before. This is, of course, a neural network, so guess what? The models that we're going to use there are going to be they're going to be neural network models. So there's going to be a kind of input, you know, to these models. It'll be like what's happened previously, and then at the end of this network, there's going to be some way of predicting these RGB values, like the next RGB value. And you know, you probably have some sense of like how this works already. This is going to be a classification problem over like total number of possible configurations per pixels, like I just described as triples. And we're going to have, you know, we're going to learn from all the data we have how to this kind of map. Yep, we need to define the ordering. We already talked about that. You can do this ordering in various ways. This paper from 2016, this Pixel RNN paper, starts from this corner, and then starts to work its way out instead of being raster scanned to be like going to the right and then down, and so forth. So a more complicated ordering. I think the reason for it is that it maybe got slightly better results, but whatever. But the point is that the way that the neural network that this model uses to do this kind of learn this dependency on the previous pixel values is going to be an RNN, it's going to be, this LSTM like we already saw, right? So the tokens here are going to be pixel values. They're discrete, like there's a vocabulary, right? There's a vocabulary over, what is that, 256 times 256 times 256. So that's some power of 2, that's kind of high. But it's vocabulary nonetheless, and that's what we're going to learn to do is like predict the next token, one of those triplets, using an LSTM. That's why it's called pixel RNN. So it can work. I'll show you some examples in just a second. But as you can imagine, there's a lot of pixels to generate in a large image, and this is actually quite slow at inference time. Yeah, what's the question?
Oh, sorry, I just was thinking with my hands.
That's good. Oh, I guess I'm not showing examples of that one. Everybody has examples. Let's find out. Just these. Okay. So, does that make sense? I mean, like, intuitively, does it make sense? We just learn about RNNs. We just port the whole RNN framework over to this, and we just treat the pixels as tokens. And that allows us to have variable length input. It turns out that we don't use every single pixel in this, right? Like we already learned that for practical reasons, you can't for RNNs you really can't learn very long dependencies, long range dependencies, so that the fixed length might look like 20 pixels back or 30 pixels back or something like that, maybe even 50 pixels back with like an attention mechanism or something like that. But you really can't look that far back. So it's not going to actually be conditioned on all of the pixels all the way back, but it's going to be on some back. And now that I think about it, that's probably the reason for this kind of ordering is that the pixels that it presents to you are they're like at any point in this ordering, you're gonna the last 30 are going to be like more or less the pixels closest to you, rather than like a raster scan. That's not necessarily the case. Questions about that? Not recommending that you go and train this model, but you could. Not too difficult. CFAR where these images are 32 by 32 by 3. It's actually not that big of a deal. Okay, then there's an improvement on this called Pixel CNN. So Pixel CNN is very much like Pixel RNN. You are trying to predict the next pixel, but you're going to use convolutional architectures. So you're going to use convolutional filters, and the way that this works is, you start off generating some of these pixels. Maybe you got to this point where you are in this case doing this kind of raster scan thing, and you got into this picture, you need to generate this one. Well, what you've been learning to do is you're gonna lay a kind of some size filter over the image that you've generated so far, and over part of the image that you haven't generated so far. That's like that's in the future. That's masked. We're not going to get any information from that. We're going to set all those to 0. But we're going to do the convolution with all the other pixels that we've already generated. And then, that's going to produce a set of scores across all of our, possible pixel values. So this is like showing for one, for maybe the red channel. We're going to need 2 more of those for the green and blue channels. But then, there's your histogram over your vocabulary, and you pick the most likely thing, and you go to the, done this beam search, and you go to the next one, and so forth. So it's basically the same as we saw with Pixel RNN, but this time we're using convolutional layers instead of the recurrent layers. Yeah, and then we basically just learn. We learn these distributions. We can compute these. We can supervise these from our. We can create the data sets from these, right? We have all the from any of our images. We can pick. We create a data sample by fixing on particular pixel in the image, and then taking, all the pixels behind it, and then, training the model to do that next prediction. So that's how we supervise it with the correct RGB value here, and we just learn to do that, and we just do that. We do that many, many times. You can imagine that each image is giving us quite a few training examples, one for each pixel, although they're quite correlated if you think about it. So there's sort of you want to sample randomly from here, but you can set this up and do this and learn to generate images. Yeah.
Yeah. So this you're talking about training time, right? During test time, once the model is trained, won't the model generate the same image every time because the seed is the same and we are generating the whole image and the model obviously generates the same distribution.
Yeah, if the seed were the same, yeah, I mean everything's pseudo-random here, right? So you can of course make it deterministic. But the point is that, you would not have the seed be the same, or you'd sample from the distribution many times, and then when you generate the next image, it'll give you something different. But you're right in the sense that because of the pseudo-random nature of how we generate random numbers, that this is more or less deterministic. That's true of everything we've done so far. Anytime there's a random procedure.
Yeah, but where do we bring randomness here? Because every time.
Well, the randomness is in a sample. This is a distribution, right? So this is exactly the same as in the language example. This is a distribution over your tokens, or in this case, your pixel values. So when we're one way to at inference time to introduce randomness is to, instead of taking the most likely value, to sample from this distribution.
Use beam search, right?
Yeah, exactly. That's exactly right. So so sample from that, and so the stochastic nature of this was going to build up in this kind of autoregressive way as you go, right? Because if there's a difference, you sample something randomly here, you have some probability of having a certain small number of configurations for your pixels in the first couple of pixels, and then as you continue to go, you can generate more and more very different images, right? Because it's autoregressive, because you're predicting the next thing given the previous things. This kind of randomness builds up, so you have quite a variety of things, especially if your distributions are really looking like what you see there, rather than very peaked around a particular pixel value.
Does this assume that all pixels surrounding the missing pixel, or could there be a conflict missing?
No, in this one, it still generates the next one.
Oh.
It still generates the next one from only those things that you've already generated. That's why it looks like this. I mean, it's maybe not the best picture from the paper, but the idea is that this convolution again is going to the filter is actually going to lay over. Think of this as being the set of filters, but it's going to only use those. It's only going to use these values for making the prediction. With the pixel that's already generated. Right. So I mean, it's literally learning to do this right here. And once you have all those, theoretically, what you've done is you've learned a distribution over the data set itself. Okay. How well do you think this works? What's your intuition? Basically, this is going to generate images with a high probability of being in the data set. So again, being in the data set doesn't mean it's going to it's literally one of your training examples. What it is it should be some arrangement of pixels. Probably you haven't seen it in the training example, but it should look like it's from the training set, right? That's the whole point here. How do you think this is going to work?
Probably be pretty blurry.
Blurry? That's good intuition. Why do you think it's going to be blurry?
That's usually the high frequency features don't get captured by the CNNs.
That's true, but why?
Because the softmax is taking the neighboring pixels and it will sort of create a point related, a pixel related to the pixels around it, and so it will be a continuous stream of similar looking pixels, so it will be particular.
It looks similar to probably the filters that we have in CNNs, because it's kind of a representation of the whole image, whole data set kind of.
Okay.
So when we train the CNN, usually it's taking the sort of average, and that kind of averages out noise that you would normally, or the high frequency features that you would normally see.
So what do you mean by the taking an average? Be a little more explicit.
When you do multiple examples, I mean, when you train the CNN over multiple examples, it kind of blurs it all together inside of the CNN, or aggregates it all together in the CNN. So it wouldn't be able to capture like the grain of the image very, very well.
Yeah, right. So, right. I mean, this is good intuition for sure. So, like, you know, what's happening when you're training these things is that, you know, it sees a certain arrangement of pixels, and then it sees, you know, like, it's followed by, like, you know, a particular RGB value at that pixel. Then it sees basically that same, like, set of pixels again, but then it sees maybe a different one. Like, especially as it's making, like, these sharp transitions, like, at like, edges, right? And so it's, you know, it's going to see lots of examples where there isn't an edge, and then every once in a while it's going to see an example where there is an edge and it needs to make a sharp transition. And it might have some context for like where to make that transition from the rest of the image. That's the whole point of, like, you know, like if you think that, like, there's like an edge right here, right? Like this thing should learn to see that, like, you know, there's an edge kind of coming into, and it would use this pixel in that edge, and, you know, it should learn to say, like, probability is very high that it's going to, like, be, you know, a pixel that would correspond to having this edge. But there are going to be other examples where that's not, you know, like, that's going to happen and it's not the case. So because these are all maximum likelihood, you know, types of learning algorithms, they try to maximize likelihood of the data, it does have to do this kind of, like, averaging over all the examples that it's seen, some of which are doing one thing and some of which are doing, like, a totally different thing. So what you get is you get a distribution of that, which corresponds to, like, a blurring of, like, sharp detail. And that's exactly what happens here. Sorry, I was going to go to the examples here. We'll come back to that point. These are really bad. I have to go look at the slides on. It's just hard to see on the projection here. But these are samples doing this pixel CNN procedure for, like, CFAR10, and then, like, for, like, a small version of the image net, where we resample to 32 by 32. Again, the reason for this is that this just the massive cost in training and in inference time in generating so many pixels. But what you can kind of see, I hope what you can see is, you know, from a distance, if you just think about the examples you've seen, like, from the actual CFAR dataset, for instance, like, these things, like, really have a lot of the characteristics in terms of, like, the colors, and where, like, blobs of color kind of are, and that there's, like, you know, there's just, like, a kind of believable, from a distance, like, oh yeah, that looks like that's probably an image of a natural scene. But as you come up and look at it, it's completely nonsensical, like, completely nonsensical. Like, nothing in here there's, like, nothing in here that has, like, any semantic, you know, kind of content at all. And what's happening is that you are seeing this kind of effect of maximum likelihood, where there's a bunch of blurring, although it's really hard to see it in the presentation here, so you have to look at these, you know, slides up on canvas. But you're also what you're having is, like, a kind of, like, blurring, or like an averaging over all of, like, the semantic content of all of those, of all the images in CFAR10. So it's like, it doesn't learn to produce a car, like the whole car, right? Because it can't learn to do that, because it doesn't learn, like, how many pixels go into making a whole car? A lot of pixels. And these things are only looking at, you know, parts of the, you know, of the image. And it's only looking at the parts of the image that kind of came before in whatever kind of arbitrary order you picked. And so it's not learning, nor do these models have the capacity to learn, like, you know, how to like, create a full, you know, image of a car, for instance, or a horse, or a boat or something, from just, like, previous pixels.
Did this start from a corner or in the middle?
Yes, like these are raster scans. So start from top left corner, and then just.
Because it seems like it's like starting to draw a car and then it just kind of forgets.
Yeah, that's exactly right.
So do we need like an attention mechanism to fix this?
Attention mechanisms won't work because you can't really even pay attention to those. I mean, you could, but like computationally you can't because it's just too much compute to look back at all those pixels. But yeah, that's what's happening here. So like it's learning to statistically it has like the right structure in terms of like color and blobs of things and like some transitions from blue to white and black to red and things like that. But in general, this is not drawing out any sort of like meaningful object because it can't. Like, it hasn't learned. It just doesn't. These models don't have the capacity to do that, which is kind of a shame, right? Because what distribution has this actually learned? Well, it's not the distribution we really wanted. We really wanted this to generate pictures of cars and pictures of horses, and so it didn't really capture that. So this is not a great way to go. And learning to overcome these limitations is a really important aspect of how modern deep learning evolved in terms of how to do these generative models. So the GANs that I've referred to a couple of times, come as one of the ways that you would try to be able to generate samples from these data sets, but to be far more crisp. There's a technical way to think about this, and then I don't have slides in this lecture, but we'll have slides later on. And that is, remember what I told you is the way to think about this is you have all the arrangements of pixels kind of laid out in this high dimensional abstract space, right? And then you have this probability distribution that's drawing modes around, or it's peaked. What's a mode is in a distribution? It's peaked around the right arrangement of pixels so that you have a car in the picture. So what's happening here is that it's not learning those crisp, very steep peaks around those. What it's doing, and this is true of MLE in general, is that it's taking all these nearby peaks and kind of learning like an average amongst all of them. So all of the arrangements of pixels kind of around there, around your examples, are as likely as the ones that actually contain objects. And so there's a kind of smoothing out over these, these really steep peaks to be kind of this more uniform distribution over any of the arrangements of pixels that are nearby. And as you can, as you imagine, you don't have to change too many pixels before your image really stops looking like a natural scene and looks more like something like this. Yeah.
Yeah. So I looked at similar to the language models in language.
Yeah.
But there we can actually see that the models are generated recent from sentences compared to what I see here. So where do you think the difference is from?
Yeah. So one is those sentences. It does well for those sentences if those sentences are 20 tokens or less, right? And here we're trying to learn these long-range dependencies that really are thousands of pixels in length. So the RNNs and the CNN version of this RNN thing, which again is this autoregressive thing where you're only relating to the past. It can't learn the relationships amongst thousands of pixels.
So you think long-range dependency is the only problem on this direction?
No, but that's one of the major problems. The other one, other problems here are in language. The statistics are a lot more. So, in images, you can pretty much find. I would guess, I haven't ever done this, but I would guess that I could pick an arbitrary sequence, maybe not too long, but an arbitrary short sequence of pixels, and I bet I could find that short sequence of pixels somewhere in an image in my data set, or something very close to it. Where that's not true for language. there are just like there are certain tokens that can't go next to each other. They just don't go next to each other. Or like a certain triplets that like they'll never go together. Like language seems to be a little more sparse in that way, in these like higher order interactions between the tokens. Whereas for pixels, it's not that way. Like it seems to be like a lot more dense. Did that make sense?
Yes.
Yeah. Okay. I think that's a really big issue here when using these kind of matching likelihood approaches. Is that you know, like basically all kind of short configurations are valid, and it has to learn how to deal with that, and it spends a lot of capacity trying to deal with that, and it doesn't do a great job. You get things like this. Good questions. Other questions? Yeah.
So when before we like are starting to generate some of these images, are we assuming that we, or whatever it is, the thing that's creating this has like seen X number of images?
Yeah, I mean, like the assumption is that you've trained this, you train this on your whole training set,
Okay.
and that the training, there's been multiple epochs of training, meaning that you've gone through the data set many times, right?
And there's no like pre-processing done to like kind of organize images before that happens, or
I mean, you
it's kind of,
could,
like,
but like, what's the beneficial thing you're thinking of here for like organizing these beforehand?
Because then it seems like maybe you would create something that's like a mix between classes, because like if different classes maybe share some attributes, they've got this green color, like it's a frog or it's a tree or something, you might get confused and like start making a tree frog or something. But if they were like separated beforehand.
What do you mean by separate? Like in different mini batches?
Or just like you kind of got all the frogs together and then the trees together.
We don't have the label stuff. We don't have label.
I know, but if there was some way to like organize them.
So this was a good point.
Like the
but you could.
Or the clustering or something. To organize them.
Yeah, so let's just imagine that you did do that. Let's imagine that you like somehow clustered these in a way that like respected this fact. Like all the there would be like a huge number of clusters here, but let's say like you take like this sequence of like 3 pixels in a row or 10 pixels in a row, however your ordering is, and you want like all of the images that have that sequence of pixels, and you put them all together. What would you do then at that point that would allow you to overcome this issue?
I'm not sure.
Like just pick one of the examples from that cluster? That's not a bad thought. I mean, we can talk about like why that might be a problem, but I thought maybe you were going there. That's why I suggested it.
Yeah, I guess I hadn't really thought like too enough about it. I was just wondering if it was like seeing something all at once, or if there was kind of like a separation happening before.
So remember that like as you're training, you're not every mini batch. I mean, there are some ways in which you correlate what's happening in a mini batch, like through batch norm, right? Batch norm like looks at all the the whole mini batch computes like statistics over that batch, and then like does something. So like that is kind of it's creating a kind of dependency on the other images in that batch, in that mini batch. But if you're like sampling IID, then like when you go through the next epoch, pick one of those images for the mini batch. It's going to be with a totally different set of images in that mini batch, so that you like overcome the kind of correlation that's created, by operations like batch norm. And so like in general, the image, like when this thing is training, it's not really seeing these things as a group. It's seeing these individual examples, computing a loss for each example, and then making taking a gradient descent step given that calculation. So, and that's just like a simple, usually just a simple average over all the losses in that mini batch. So there's no correlation there. So I think the intuition that you're saying here, there's probably some way to smartly sample as we're training, maybe prune the data sets in some way so that you don't get these confusing examples or whatever. There might be some kind of a kernel of a really good idea there. But in general, this is just, there's a way of computing a loss per image, and you're just, you're taking gradient descent step with respect to that signal. I love the thinking. I like the deep thinking here about trying to think of the mechanics here and what's going on and why, how do you overcome problems like this? Because of course people were thinking a ton about this. How do you overcome these problems?
How exactly are you doing backpropagation if you don't have labels in this case? No.
Well, there is a kind of supervision, right? You're learning to produce the next RGB triple, which is your token. So there's a classification loss. Either that's
so the
right
image
or
is
not.
practically its own label then.
Yeah. So we call this unsupervised, but you really truly can't train a neural network in an unsupervised way. There has to be a kind of signal for the loss. So people started calling these kinds of things self-supervised. There isn't a label, but you're using the data itself as a label.
So is unsupervised and kind of a misnomer?
Well, kind of, just from these examples. There literally are ways of doing unsupervised machine learning that don't make this confusion because they're not neural networks.
So why don't we just have the image at the bottom of the neural network? It goes in, and then it comes back out and it has the image again.
Yeah, that's what autoencoders are. And that's that's another family of things that we're going to talk about next.
An RNN seems like it's going to take forever to do anything.
Yeah, it takes forever, and it's the inductive bias of an RNN, or this this pixel RNN, this pixel CNN, is not the right inductive bias for learning to produce, for instance, things from CFAR or imaging. It just isn't.
So has anyone tried transformers then?
Oh yeah. Yep. Okay. Great discussions. We're not quite at the end of the class, but we're at the end of this lecture, so we'll end early. Pixel RNNs, pixel CNNs. So, some pros. I guess it's a pro. We're explicitly computing the likelihood. Maybe that's useful. You can use that for maybe doing outlier detection or something like that. Although, truly, you can get so tricked by these models. So, probably not a good idea. But hey, you have an explicit representation of the likelihood. You can, as you're training, it's very clear what you're doing, how to evaluate. You know how well you're doing. A cross entropy loss that you're using here, expresses things in bits. There's a lot of understanding here. It says that these are good samples. I mean, they're not good samples. We just criticized them for a long time, but they're good samples in the sense that they're a lot better than what came before. But in particular, cons here, the sequential generation is really slow, and these long scale dependencies that you need to generate a true object just can't be learned by these kinds of models. So there's lots of attempts to improve on these things using lots of other kinds of tricks from different kinds of convolutional layers, different ways of thinking about the loss, all these kinds of other things. But in general, these don't end up producing very crisp images, and we want to take totally different approaches to this, and that's where we're going to go next.
Yeah, I think one of the problem is the pixel distribution may not be. It might be a Gaussian mixture model or something, but it has so many pixels. It's a distribution that has so many pixels, and that's why when you max out one pick, it's actually average out.
Yeah. No, I was trying to. I need a better picture. I mean, I need a picture, not a better one, just any picture. But it really is that. There's a ton of peaks in this probability distribution, and they're really near each other. And you don't have to change too many pixels where all of a sudden the probability drops to 0. But these methods can't learn that. They sort of average over all of that. And that happens often in maximum likelihood types of approaches to training. So they don't do a good job of learning these very narrow, steep modes in your distribution.
Yeah.
They average over. You like average over all of them. Okay. So yeah. So that's it for today. We'll talk about autoencoders next.